Now it's my pleasure to welcome to the stage Aaditya, Purani, and Max Garrett.
Good morning, everyone, and thank you for coming to our presentation. Let me ask you this. Have you ever wondered how secure it is to open a message within the desktop app you use to chat with your colleagues at work? Have you ever thought how secure it is to open a source code which you just downloaded from the internet within your favorite source code editor? What do these Electron-based desktop applications have in common, and how fundamentally secure are they? Before a year, we set out to find an exact answer to discover what lurks beneath Electron applications, and throughout the course of 1 year of our research, we were able to compromise multiple iconic applications used by millions of people, and were able to find an hidden attack surface within Electron. Hereby, I welcome everyone today to ElectroVolt, where we will take you on a journey to pwn popular desktop applications while uncovering new attack surface on Electron. So the agenda for our talk today is I will go through the basics of Electron and its security settings. Then we will hack some real-world, commonly used desktop applications, starting from the least restrictive to the most restrictive security settings. And then I will present the novel attack vector we discovered within Electron.js framework. And at the end, we will talk about the mitigations. So let's get started. So who are we? I'm Aaditya Purani, AKA Napstack. I'm a senior security engineer at a leading automotive company. My main area of expertise are AppSec and blockchain. And on the weekends, I play CTFs with Perfect Blue. Joining me today is my colleague Max, who is a security researcher at AssetNote. Max's area of expertise are AppSec and blockchain, and he plays CTFs with Water Peddler. So what is Electron? If you can build a website, then you can build a desktop application. That's the main concept behind Electron. So Electron is a popular open source framework which is used by many commonly used apps, such as Microsoft Teams, Discord, Slack, and other. Fundamentally, Electron is built on top of Chromium and Node.js, which means that by just using JavaScript, HTML, and CSS, you can ship an entirely cross-platform native desktop application. Before diving into the bugs, it is important to understand the architecture of Electron. Within Electron, there are two types of process. The first one is the main process, and the second one is a renderer process. Main process is the starting point of all the Electron applications. Main process can create multiple renderer process using a class called browser window. It also has access to native GUI APIs to create objects like menu and tray. And it is important to note that there can be only one main process. On the other hand, we can have multiple renderer process. And the main function of a renderer process is to render a web page using Chromium. So as Chromium is used, a lot of Chromium-related features are used, such as Chrome site isolation, multiple process, etc. The way the main process and renderer process talks with each other is through something known as IPC, or Inter-Process Communication Module. And you can also apply a lot of security settings within the browser window configuration within a flag known as web preference. So that way you can control what type of renderer process you want. The least restrictive you are, the more vulnerable you are. So let's see how it looks in the code to get a bit idea about that. So here we have a file known as main.js. It sets up a browser window, and within the web preferences, it lists down a couple of security settings, which it sets true or false. Then it loads a URL, which is the web page you want to load, which is google.com in this case. And then it defines an IPC main, which is like an event listener to listen for IPC call. In this case, it's open URL. On the other side, on the renderer process, it is divided into two parts. The first one is preload.js, And preload script contains code that is loaded prior to the web page. So preload script run within the renderer context, but are granted more privileges by having access to Electron or Node.js API. Context bridge, which you see in the slide, is a way to safely expose an API to the web page, which could be later invoked using a window object. So here we have a web page, which is hello world, and the web page uses the window.electron.open URL and supply argument to pass it to the IPC main.event listener. So as we can see here, you can put whatever security features you want to get whatever renderer process you want. So the least secure you are whenever you use like something like sandbox is equal to false, context isolation is equal to false, and node integration is true. Because in this case, the web page has directly access to the node primitives. And in this case, XSS is equals to RC, because someone can just do a require child process and exec whatever shell commands they want to do. Electron developers also thought about this, and they came up with something known as context isolation. So as you can see in this slide, in the renderer process, now we have two separate contexts. The first one is the application context, where the application JavaScript runs. And the second one is an isolated context. And within this isolated context, the preload.js, which we saw earlier, and Electron's internal code would run. So it is completely isolated, and the web page now doesn't have direct access to node primitives. So this is the same concept used in Chrome as well. In Chrome, it is called isolated world, where the extensions content script JavaScript is different from a web page JavaScript. So there is an isolation here. So throughout our talk, the attack surface is the renderer process. So we will be starting by abusing the least restrictive Electron configuration, and then move on to the complex exploits. So to keep the slides clean, let's keep in mind the following terminology. So we have node integration, context isolation, and sandbox. And don't worry about the node integration in workers or node integration in subframes yet, because I haven't talked about it, but we'll talk in the coming slides. So the first situation, node integration is true, context isolation is false, and sandbox is false. This is as insecure it can get. So it is really easy to get a shell, as node is directly exposed to the renderer. The only thing you need to do as an attacker is to find a way to embed a JavaScript within the web view. So within the diagram, the circle marked as red is where we are targeting currently. So I'm going to present one of the case study which we found in a real-world commonly used application known as a VS Code. So VS Code is a source code editor where you can open a project and you can navigate and browse through the source code. So VS Code had a feature where it asks before you open source code that do you want to open it in a restricted mode, or do you want to not open it in a restricted mode? So as a part of this use case, we found a way to perform a remote code execution in VS Code in the restricted mode. And so as a part of our attack vector, we had a limited XSS, and we turned into a remote code execution chain. Let's see how it works. So this is like a pretty large schematic of how the exploit looks like. So we have 3 frames here, which are marked by the square symbols. So the one which is in green is running with the most strict Electron setting, whereas the one in the red is the one which we just talked about, where node integration is true. So as an attacker, you have an XSS on the markdown previewer, which is running in a very restricted context. And the goal is to move from that green to red somehow. And let's look at how we can do that. So first of all, let's say if you open a markdown like pwn.md, as this is subject to a strict CSP policy, what you would do is you would perform a meta redirect to an external website. And once you are on the external website, you can run any JavaScript you want. So once we had this XSS on step number 1, what we do is we leak the extension ID of VS Code. As you know, you can install extension in VS Code. And those IDs are a pretty long string, which you cannot guess. So once we leaked that extension ID, we found an XSS on one of the other window, which is VS Code Web View. And what we did is we found a way to perform a post message call to that particular frame. So in this case, we deploy our XSS using a post message on VS Code Web View. And then we deploy another XSS on the same web view to perform a channel do read, which will leak a current directory where the project is downloaded on the victim's machine through VS Code file. So VS Code file is a file is similar to a file protocol, but the catch here is you can invoke it from a different origin. Not from the same origin. So once we leak the directory, what we do is we perform a path reversal on the VS Code file by doing .. the path to an HTML file within our project. And this HTML file, what you can do is you can do top.require to get access to node primitives and pop a shell. So let's see how this looks in the demo. So our victim has opened a project in a restricted mode, and they will navigate a file. And as we can see, we have popped a calc in VS Code, which is the remote code execution part. So we received $6,000 bounty for this remote code execution bug in VS Code. And we had a really prompt and swift response from the Microsoft team for this. Let's move on to the second case study. In this case, let's increase the level of restrictiveness a bit. So we turn on the feature which is called context isolation to true, which was false in the previous scenario. And if context isolation is enabled, then node is not directly available to the renderer. So you just cannot do require child process and pawn a shell. So there are two ways to exploit this. First one is you can use a Chrome V8 renderer exploit because sandbox is disabled. So you can go to like a CR bug and look for a crash POC and get your own end day. Or you can try to find a way to disable the context isolation somehow, which we'll be talking in the coming slides. So in the schematic, let's go again. So we have an XSS on the application layer, and this time there is an isolation between where the node and Electron API resides. So the previous attack won't work here. So the second case study we have is a remote code execution on Discord, which is a commonly used application. We found that Discord was using an older version of Electron, which was 12.14.1. And this means that it is also using an older version of Chrome indirectly, which is 83. So when we were looking for attack surface in Discord, the most interesting one was a video embed. So let's say if you send a message to a victim on Discord with a YouTube link, you will see that the video will get expanded and someone can click on it. So we found an XSS on one of the third-party embed, which is Vimeo. And we used that to get our initial JavaScript execution on Discord. But the catch here is whenever there is an iframe in Electron-based application, it is sandboxed by default. So we cannot just simply run like a renderer exploit of Chrome 83 and get an RC. So we dig down deep in the Discord, and what we found that we found a misconfiguration in a new window file handler, which can be used to open a new window using window.open. And this new window had a sandbox disable. So what you can do is you can open a window with a location of an external website controlled by you, and then you can run your Chrome V8 renderer exploit to get RC. Let's see the demo. So attacker is sending a video link to the victim. Victim will go and press on it. And as you can see, this is the new window which I talked, which is without sandbox. And you can pop a calc on Discord. And this can be done improvised by just putting style sheet to make it more lucrative and conduct social engineering attacks. So we received $5,000 bounty from Discord. And Discord fixed it by upgrading to the latest Electron version and fixed this new window misconfiguration by limiting to not have redirection to external website. And most of you already know about this attack. It's common knowledge to use a V8 exploit when sandbox is disabled in Electron app. But what I'm showing you is it is really common in real-world applications to have this sort of misconfigurations. Let's go one step further. In this case, we turn sandbox to true, but now we have context isolation to false, which was true earlier. So as sandbox is enabled on renderer, we cannot directly run like a Chrome and exploit to get RC, because this time seccomp or Win32k lockdown will stop us by blocking bad syscalls. As node integration is false, no node modules are exposed to the renderer, so you cannot do the trick in the first slide which I mentioned. But now the catch here is there is no isolation between the website you load and Electron's internal code or preload code. In the diagram, now you can see we had two isolated contexts before, but now there's this one block which runs Electron's internal code, your application, and the preload. So Electron's internal code is written in JavaScript as well. So what can you do with an XSS? Can you do something like prototype pollution to overwrite Electron's internal code? Let's see. So how to get a shell? So if the version of Electron app is less than 10, then you can use prototype pollution gadget to leak remote module or IPC module. So remote module, according to Electron documentation, is a module which is used to bridge JavaScript objects from the main process to the renderer process. So once you have access to remote module, even in a sandbox window, it is trivial to get access to node primitives using it. For Electron version 10 to 14, Electron developers thought about this and they disabled remote by default. So they toggled the true to false. So you can still try to leak the remote if application developer has enabled it explicitly, or you can find an IPC misconfiguration. For Electron version greater than 14, which are like the newer Electron version, remote is completely deprecated due to this security concern of how it can allow you to give node primitives on a sandbox window. So you can still use a prototype pollution gadget to leak IPC module. But in this case, what you can do is, after leaking this IPC module, you need to find misconfigured IPC within the web app or within Electron's internal code. So what I'm showing you here is a novel prototype pollution gadget we discovered on the latest Electron version. And this concept of prototype pollution is not unknown. It was first presented in 2018 by Masato Kinugawa on an older Electron version. But this is something which works even on the latest version. So as you can see, we override certain inbuilt JavaScript function, which is call and ends with. And then we, on the number 3, we get access to webpack require, which contains all these modules which we want to use to get RC on your favorite apps. So for a situation like this, where sandbox is false, you may be wondering you can just run a renderer exploit, but you can leak this webpack require using prototype pollution and also get access to like node primitives or Electron common API to pop your calc. And you may be wondering why to use this and not a V8 exploit. And the reason is this is much more reliable compared to a V8 exploit, for example. A second reason is that you don't require binary exploitation knowledge in order to perform this attack. It's a complete web attack. And the third reason is, what if the application you are targeting doesn't have a Chrome end in the first place? Then you need to be creative and use something else. So for an example where sandbox is true, you cannot get access to the node primitives. But what you can do is you can leak Electron's IPC binding. So you can leak two IPCs, which is IPC renderer internal and IPC just for Electron's internal IPC. And then you can invoke multiple developer-defined IPC channels like OpenURL, which I showed you earlier. Or you can invoke Electron's internal channel like Electron star or guest star. So let's take a case study for Microsoft Teams where we were able to achieve local file read and were able to perform an account takeover on Microsoft Teams user. So Microsoft Teams was using Electron less than 15. We found an XSS in the renderer where you send a message to someone using a 0-day in CK editor. So we perform a mutation XSS in Seq editor, which was a zero-day finding which we did. And this is something which is used as a rich text formatting for Markdown in Microsoft Teams. So once you had this XSS, what we noticed that when you open a new window, context isolation is disabled, but sandbox is enabled. So we can use that same attack vector which I showed earlier. So we use prototype pollution gadget to leak IPC using our XSS. And once we leak IPC, we leak the Electron's internal IPC, which is IPC renderer internal, to make an IPC call to a browser process which reads a file given a path. So think of it as like a file read or local file inclusion attack. And this was a misconfiguration within Electron, which was fixed in the Electron version 15. And as you can see, you can perform an IPC invoke with this Electron's internal API and supply a path name. So let's look at the demo how this is going to work. So this is where we have our XSS. And on the attacker's website, we can see that we leaked the file, which is desktopconfig.json. And within this file, there is a JWT or JOT token, which you can use to get access to any user account which you want to target. So that is the impact of our Microsoft Teams exploit. So we received $3,000 bounty for our Microsoft Teams exploit, which is pretty nice. But let's take one step even further. What if everything is green? Like, what if an app is running with all proper security settings? So this settings is used by most of the application. Node primitives are not exposed to the renderer. Context isolation is enabled, so we have a separate context, and sandbox is true. So to hack this configuration is the main part of our research. So here in the block diagram, we are mostly targeting this sandbox renderer portion. So at this point, you might have a question that, is this just like having an XSS in a browser because everything is enabled, all security settings? And the answer to that is no. The reason for that is that Electron is not the same as your commonly used day-to-day Chromium browser, for example. So Electron code is something which is a combination of Chrome and Electron-specific code. So what if we find a way to abuse this intersection between Electron's code and Chromium code and somehow subvert all the defenses which Electron had? Let's see. So first, I'm going to present a CV which we discovered in Electron, which is enabling node integration in subframes from a compromised renderer. So what is node integration in subframes? So let's say you have a website, for example, .com, and you create an iframe within that website, which is to load another web page. Now let's say if you want to provide access to node primitives or preload scripts within this iframe, you need to enable a feature flag known as node integration in subframes, because by default, it is false. So this is a way to provide access to preloads or node primitives to your iframe. So for every subframes like iframe or child windows, if node integration is enabled and sandbox is disabled on your parent window, which is your example.com, then Node.js primitives will be available in subframes. If node integration is disabled and sandbox, doesn't matter even if it's enabled or disabled, then all your preloads will load within this specific iframe. So let's see in the code to understand a bit further. So here we have a main process where we create browser window preference, and node integration in subframes is false. We do the same thing, load a URL, google.com, and define an IPC channel. On the render process, again, the same story. We expose open URL. And on the website google.com, I create an iframe to pwn.af, and I use that window.electron.open URL to pass an argument. This works fine. But from the iframe, when I try to do the same thing by invoking that open URL, it doesn't work. It's because node integration in subframes is false. Let's turn it to true. And in this case, no error is thrown, and you can pop a calc from your iframe. So most of the time, when we get XSS in a lot of these applications, it is within iframe or subframes, which you noticed in the Discord earlier. And in this case, node integration in subframes is disabled mostly because developers do not go against the design pattern and enable it unless it's needed. So in this case, even if we have access, we don't have access to context bridge exposed API on Mbed, which is a bit sad. But can we still hack it? Can we still find a way to somehow get access to those preload and node primitives through this? Let's see. So to see this, we take a deep dive into the Electron source code. Let's look at how Electron implements these security features. So what Electron does it patches Blink web preferences and adds this node integration in subframes, context site isolation, everything within this. So in the red, NISF is implemented there. So when we take a more deep dive into how the code for this works, like based on what you need to enable NISF, we can go to a file which is in the folder, which is shell renderer. And within this file, what it happens in the box marked as red is the renderer frame gets access to Blink web preferences, and then it accesses node integration in subframes variable. And if this is set to true or false, based on that, it will make a decision on whether to enable that feature or not. Now, if you have been paying close attention, you would notice that the check here for this feature is on the renderer process. So what we can do is, if we can run a renderer v8 exploit and find a way to somehow set that variable which we just saw previously to 1, then we might be able to enable NISF. So here is an annotated version of our binary exploit. So first of all, we leak address to window in the memory. We add it to get access to web preferences. We add an offset to node integration in subframe, and then we flip it to 1 from 0 to enable it. So this is how the changes which you would make to your v8 exploit in order to perform this attack. So let's look at the real-world case which we found in Element app. And Element is a really famous application. So it is using Chrome 91 and Electron 13. There is an XSS on Mbed through a deep link misconfiguration, and no context bridge API on Mbed is exposed by default. So what you can do is, same story, you run Chrome v8 exploit, expose context bridge API, and then perform your exploit. So within the main process, Element app defines IPC known as user download open. This is used to open a path using shell.openPath, which is a dangerous sink in Node.js. And on the renderer process, it exposes electron.send as a way to proxy messages to main process. So as we can see in our exploit, what we do is we create an iframe src doc to create your own iframe. And once this renderer exploit runs, it will create this iframe with node integration in subframes enabled. So within this new iframe, you will be able to access like electron.send method, which was exposed earlier, and can pass your own argument to pop a shell. So iframe will pop up, and then you can pop up shell because NISF is enabled. Let's see how this looks in the demo. So victim opens the app. It's a video conferencing. Victim will try to join this video conference. And as you can see in the background, I want to show you how this exploit would run. This is where this calculation of the offset is going to take place. So we are doing a step-by-step calculation. And once this happens, the shell will be popped, as now you have access to those preloads. So now let's try to do it a bit more. So we received a $3,000 bounty from Internet Bug Bounty Program as we reported this bug to Electron.js. So now we will try to disable context isolation using a compromised renderer. So in this case, it's the same story. You know that Electron patches Blink web preferences, adds context isolation there. And when we look into the Electron code, what we figure is it does the same thing. It gets access to the web preferences and access context underscore isolation variable in the step number 1. In step number 2, it has a Boolean value, which is like should create context isolation, which is based on the value from the step number 1. And on the step number 3, there is a if statement, which is like if should enable context isolation is true, then enable it, else disable. So our goal is to disable the context isolation. So same story, you can use V8 renderer exploit, because this particular feature was enabled on the renderer side and not on the sandbox side, which was a design flaw within Electron.js framework. And then you can set it from 1 to 0. So this is an annotated version of our binary exploit. We get offset to a CISO in the memory, and then we overwrite its value from 1 to 0 to disable it. So let's take a look at our final case study, which is RC in an undisclosed app. So we found a feature to embed untrusted content in an iframe in this application. So in the main process, again, you can see open_external is a channel, which is dangerous sync. And on the preload, we have something known as isAllowedURL, which is a function to perform like allow list. And it will only allow if the URL has a protocol which is HTTPS. So unlike previous exploit, you cannot pass something like file, path to calc.app, because then it will have a file protocol, which will not be the HTTPS. So let's try to find a way to bypass this and make a direct IPC call to the main process from the web page. So here is our exploit. First of all, we disable context isolation using our V8 exploit. Then we perform a redirection to another web page, which is leak.html. And once this page is reloaded, this will be reloaded with context isolation disabled. So what we can do is we can perform prototype pollution, which I showed earlier in the previous slide, and get access to the IPC directly. So in this way, you can make a call even with 5 protocol by bypassing that preload, which was the middleman performing that allow list check. So let's see how the demo would look like. So here are the calculation for the heap offset for the V8 exploit, which I mentioned earlier. And as you can see in the background, this is what it happens. It gets the offset, it gets CISO, and it sets to 0. Now this is leak.html. When we click on it, we pop a shell, because that was with CISO disabled window. So we received $5,000 bounty from this undisclosed bug bounty program, which is a very commonly used app as well. Now let's shift our gears to talk about same-site origin spoofing. So within Electron app, let's say if you want to load a website known as main.example.com, then Chromium will internally create a process, for example, a process 1 for this. Now within this main.example.com, if you want to implement like iframes, for example, youtube.com and sandbox.example.com, then let's see how many processes it creates for this two iframes. So it only creates a separate process for youtube.com, but it doesn't create the separate process for sandbox.example.com. The reason is that Chrome uses the same process if your top-level domain is the same. So in this case, example.com is the common between both of your subdomains. And site isolation won't apply here. So Chrome uses the same process for both the pages. So let's say if you have an access on sandbox.example.com, and you want to access like those preload APIs and node primitives which are running on main.example.com, then how would you do it? The way you can do is you can run like a Chrome renderer V8 exploit, and you can set document.url to main.example.com and security context origin port to 443. This way, you can masquerade as your parent page and will be able to access all these preloads and node primitives which are provided to the main.example.com. So as we notice, we used a lot of V8 exploit to perform these attacks, and there is a noticeable patch gap within Electron apps, and Chrome, which makes a lot of this app susceptible to these attacks. And if you want to go one step further, you can also use like sandbox escape from Chromium, which are pretty rare, but it can also bypass this sandbox true configuration. So as a part of the mitigations, what are the suggested mitigations for this is the findings which we did earlier were all fixed by Electron, and we were assigned CVE for those findings. So Electron made a code level fix to not do this check on the renderer process, so you cannot just directly invoke those leaked IPC on the newer version. But as a developer, what you can do is you can still enable all the security flags because that's the recommended part. You shouldn't use a untrusted third-party embed which doesn't have a good security track record. For example, we saw with Discord, like you can embed a Vimeo which had XSS, and that was the failure point for the app. So make sure your patch gap isn't large with Chromium and your Electron app. So if you have an organization and have a capability, you can fork Electron and you can cherry pick commits which are V8 bugs and can fix it by yourself. So that is one way to do it. And another issue is you shouldn't implement sensitive IPCs like what we saw earlier, those dangerous JavaScript sinks in your main process, because attacker will find a way to get access to those IPCs, even if they are restricted. And mitigate security issues across all your asset. So your main domain, your subdomain, whatever you are using in the app, make sure it is restricted, because as you saw with same site origin spoofing, a sandbox domain can also get access to those privileged context bridge exposed API. So as a part of Epilogue, we were able to compromise more than 20 commonly used Electron applications. These were running at the latest version. And we were also able to compromise JupyterLab, Mattermost, Notion, Basecamp, and the apps which I showed in this demo, which are a few of them. So as a part of our Black Hat soundbite, I want to talk and emphasize on 3 key takeaways for this. So the first one is for bug bounty hunters and security researcher, which is to dig deeper into the framework you are auditing and to not limit yourself only to the application layer. So what we see with Electron is there is a design flaw where these features were enabled on the renderer, for example, and that intersection was not done perfectly. So design layer flaws can enable you to bypass a lot of security settings if you have a primitive to tweak those. Second is for RAID team operators, that Electron apps are an ideal adversarial target, because users will click anywhere or open any link. Users are going to join video conferences. They are going to opening the messages. So if you are on a detection team, make sure that you also consider Electron applications used within your organization as a part of the threat model. The third one is to minimize attack surface on your application as much as possible. So in security, what we consider open URL redirection, it's a very P5 issue. But in Electron.js, someone can still use an open URL redirect to their own external website and get access to the main web view and perform this attack. So treat all the security issues with higher scrutiny if possible. And when you are doing threat modeling of your Electron applications, consider all the windows and apply all the security settings on every window. Because as we saw with VS Code, we were able to jump from the most restrictive to the least one and was able to get RC. So that's pretty much it for the presentation. First of all, I would like to thank everyone coming by and stopping by and hearing our talk. And if you want to understand all these use cases which I mentioned here, the application part of it, how we achieved in details, and if you want to secure your Electron applications, please visit electrovolt.io, and then you can find like our blog website, which is blog.electrovolt.io. And we have already published use cases for VS Code and Discord RC there, where you can look this entire chain in detail and understand further. So with that, I'm concluding the talk and opening up for any questions which you may have.